Hello everyone, I'm Vishal Pallagani, one of the organizers of the lab on harnessing large language models for planning. In this video, I'll be giving a code walkthrough of how Plansformer is built. So, assuming that you are on the GitHub repository for the lab, and in this video, we'll be talking about the part 4, which is Plansformer. So go to the associated module here and you can open the current notebook that I would be talking in this video, which is Plansformer Fine-Tuning CodeT5. So if you click on the open in collab, it should take you to this particular link, right? Once you are in this link, the first thing that you want to do is click on runtime, change runtime type and select the A100 GPU, click on save, and it should show an option as connect over here, which you would select and be connected to the GPU circuit. Once we do that, the next thing we want to make sure is upload the appropriate training data set that we would be using to follow along this code. So you can right click in this space and click on upload. And in the part 4 itself, in the data subfolder, you would have the train data set which you can upload. I have already uploaded it over here. So once it's uploaded, you can just use it in your code. Right. Now let's talk about each code block step by step and try to understand as to what is happening here. So this first code block that we are seeing is about installing necessary Python packages for your project. And we'll go through the detailed explanation of what each line is doing here. So pip install sentence piece is technically installing the sentence piece library. And sentence piece is a library for text tokenization, which is crucial for models like CodeT5 that rely on subword tokens to process text data efficiently. It enables the model to handle unseen words by breaking them down into known words. So this is another GitHub repository that is completely dedicated for sentence piece, and we can look at the description of it. It basically is performing byte pair encoding, and that is how all T5 based variant language models are built upon. So if you want more information about sentence piece tokenizer, you can go over here and have a brief look at the README file. So going back, one might ask, why is tokenization important for building Plansformer or any language model per se? So tokenization is a pre-processing step where text is divided into meaningful units, such as words or subwords. And it is essential for natural language processing models because it transforms raw text into a format that the model can understand and process. And we are using sentence piece in this particular code block because we are working with CodeT5, which is optimized to work with the sentence piece tokenizer because of its prior training process. While you might technically use any other tokenizer that is out there, it could affect the model's performance because the tokenization must match the one that is used during the model's training. The next package that we are installing is the transformers. So we are installing transformers library that is released by Hugging Face. And this library provides access to thousands of pre-trained models designed for various NLP tasks, including CodeT5 that we'll be specifically looking at in this code. It also offers utilities for model training, fine-tuning, and inference. Right. And if you have the question as to whether you need to always install transformers for NLP projects, that is not a necessity. It is highly recommended for projects involving state-of-the-art language models, and especially for tasks such as text generation, translation, and classification, so that you're using the latest language models that are open sourced and available. The next package that we are installing is Rich. So installing the Rich library provides additional support for Jupyter notebooks, and it is needed because Rich helps in rendering text in a beautiful format so that it is more readable for the end user. And Rich is not at all necessary for the training of the language model or any neural network. all it is doing is improving the look and adding color to the output that we get in the Jupyter notebooks. All right, so let us just execute this code block and click on run anyway. Right, I already have installed these particular packages. If you do not have this in your particular notebook, then there should be some install messages. If not, the requirement should already be satisfied. So the green tick shows us that this particular code block executed without any error, and we can move on to the next one. Which brings us to this particular code block. And this code block is responsible for importing various libraries and modules necessary for preparing data, model training, and enhancing output visualization. Let's break it down step by step so that we understand each import functionality that is being used here. So the import OS is used for interacting with the operating system, such as file paths management, and importing NumPy. We are adding support for large multidimensional arrays and matrices, along with a collection of mathematical functions to operate on these arrays. This is essential for numerical computations. And then we have pandas, which offers data structures and operations for manipulating numerical tables and time series. It is widely used for data pre-processing and analysis. Then we have PyTorch and its related utilities. So the main PyTorch library is used for deep learning. It provides tensor computation with strong GPU acceleration and deep neural networks built on a tape-based autograd system. Then we have the torch.nn.functional, which contains functions for building neural networks, such as activation functions, loss functions, etc. Then we have torch.utils.data, and it has a bunch of utilities underneath it. These utilities help in loading and preparing data in a way that is efficient and easy to use with neural networks. Dataset, which is this particular module here, it's a way to define your dataset, and data loader is a way to, it helps in loading the data in batches, and the samplers, both random sampler and sequential sampler, define the strategy to read data from the dataset. Then we have the Hugging Face transformers itself. We are importing the Robota tokenizer and T5 for conditional generation. Robota tokenizer is used for tokenizing input text in a way that is compatible with the Robota model, which CodeT5 is based on. And T5 for conditional generation is a model designed for tasks that involve generating text conditionally. Examples can be summarization, translation, etc. Then we have some modules which are based on Rich. And if we want to go through these in detail, which do not actually have an effect in the training procedure as we have discussed, but to have an overall understanding at what is going on. So rich.table allows creating tables with rich formatting. So it is more beautiful and more readable for the end user to understand the information that is being printed on the console. And the other one is box. So box provides drawing characters for creating boxes around text or tables. Then we have rich.console, which enables writing rich text and controlling its formatting to the console. Then we finally have the CUDA, which we are basically using to get the GPU access to train the model on. So one might have a question as to why we are using the Robota tokenizer in a T5 setup or in a CodeT5 setup. So although T5 and Robota are different models, CodeT5 uses a similar tokenizer to Robota. This is why Robota tokenizer is used for pre-processing text for CodeT5 models. Excuse me. Right. So let's execute this block as well and see its output. The green indicator here shows us where the current line of execution is at. All right, so we executed this particular cell as well. Then we move on to the next part where we are reading the data set, which we have uploaded. So the pd.readCSV function is part of the pandas library, and it is designed for reading data in CSV format into a data frame. A data frame is a two-dimensional labeled data structure with columns of potentially different types, similar to a spreadsheet or SQL table. So this particular function takes an argument of the file name, which is the same file name that we have used here that I have added here. So let's run this particular code as well. And right. So one thing that you need to make sure for successful execution of this code block is that you want to ensure the file path and name are correct. If the file is not in the same directory as your current notebook or script is, you'll need to provide the relative or absolute path to the file, so the execution is happening without any error. Right. Let's move on to the next code block. All right. So here we are defining a rich console logger. This code block is about setting up a logger using the rich library for enhanced console output, and also defining a function to display pandas data frame in an ASCII formatted table. Let's break down each piece of code that is present here and try to understand it. So when we are doing console equal to console record equal to true, we are trying to initialize a console object from the rich library, enabling enhanced console output. The record equal to true argument that we see here, right here, indicates that the output should be recorded in memory, allowing you to export or print the recorded session at a later stage. Then we have the display df function, which is basically used to display data frame in ASCII format. Right. So this particular function, to provide some more context, creates a new table object with two columns, source text and target text, right? Indicating the structure of the data set that we have created. It then iterates through the data frame, adding each row to the table. Finally, it prints the table to the console. Then we have the training logger setup over here. And its purpose is to initialize a table object to log training status updates, including epoch number, steps, and loss. This setup aims to provide a clear and organized way to monitor the model's training progress. The table includes three columns for epoch, steps, and loss, with each column centered. The box.ascii, which is what we see here. This particular option is used to draw the table using ASCII characters, making it compatible with any console environment. So you can run this piece of code anywhere, be it on terminal or be it on a notebook. You would see more readable output. So let's execute this as well. And we successfully have run this particular cell too. And we have already connected to a GPU backend. And that is technically what we are doing in this line of code. We are saying if CUDA is available, then please make use of CUDA. That is the GPU, which is A100 that we are using as the device for doing all computations. If not, then use the CPU that is by default. So let me execute this piece of code as well. All right. Then we come to the main series of codes that are involved in creating the data set, training, and validating the model. So this particular code is for creating a custom data set using the dataset class. Let's go through the code in detail to understand step by step. Right. So first, we have the class itself, which is inheriting from the dataset, a core PyTorch class for handling datasets. This inheritance requires us to implement both the length function and the getItem function, which I'll talk about in a minute. Then we have the constructor, which is init, and its purpose is to initialize the dataset with a data frame containing the planning data, a tokenizer for pre-processing the text, length for source and target sequences, and column names for source and target text. The parameters it takes are data frame, data frame, the data source in pandas data frame format, tokenizer, which is an instance of a tokenizer compatible with the model that we chose, which is CodeT5, and is responsible for converting text to tokens. Then we have source length and target length, that is maximum length for source and target sequences to ensure uniformity and manage computational resources efficiently. Then we have source text and target text, that is column names in the data frame for source and target text data on which we want the model to be trained on. Then we have the length method, which is basically returning, which is returning the number of items in the dataset, allowing PyTorch dataset data loader to determine the dataset size. Then we have the get item method, whose purpose is to fetch a single data point from the dataset. This method is called by data loader to retrieve batches of data, which will be used during training. And the process that is involved is it extracts and cleans the source and target text for a given index, right? It then tokenizes the text using the provided tokenizer, ensuring they are padded or truncated to the specified maximum lengths. It then converts tokenized text into tensors, preparing them for input into a neural network. Then it returns a dictionary. So this particular block of code, it returns a dictionary containing source IDs and source mask, which are the token IDs and attention mask for the source text, the target IDs and target IDs by, which are the token IDs for the target text, duplicated here for use in different parts of the training process, that is as inputs and labels. All right, let's execute this block of code as well. All right, then move on to the next one, which is the training. All right. So this particular function train is designed to train a neural network model, which in our case is CodeT5 base on a given dataset for a single epoch. It is part of a larger training loop that we'll get to see in a bit, where this function is likely called multiple times. So this is very important. I mean, this is where the main training of the model is happening. So let's go through this particular function step by step. In order to perform one epoch of training on the model using the provided data loader, tokenizer, and optimizer, it updates the model weights based on the computed loss from each batch of data. The parameters that the train function is taking are epoch, which is the current epoch number, and this is used for logging. The next is tokenizer. So the tokenizer is used for pre-processing text data, as we have talked about it before. The next one is the model, where we pass the neural network model being trained. Then the device, which we have already set it to as GPU in the above mentioned code. Then we have the loader, which is the data loader providing batches of data that we have just discussed. Then there is the optimizer, which is the optimization algorithm to adjust the model weights accordingly. Right. So let's move on to the inner loop. We have the model.train here, which ensures that the model is in training mode, enabling features like dropout. Then we have the batch iteration that is happening in this for loop. So here we are looping over each batch of data coming from the loader. And the enumerate function is used to keep track of the number of iterations. So here in this particular loop, we are mainly tasked with preparing the target data, that is Y, which is the batch of target token IDs moved to the correct device. Then we have Y IDs, which are the decoded inputs created by removing the last token from Y, ensuring alignment for sequence to sequence prediction. Then we have LM labels over here, which are the labels for computing loss created by shifting Y one position to the left. Tokens equal to the padding token are replaced with 100 to ignore them in the loss calculation, which is the convention used in many NLP models. Then we prepare the source data, which is IDs. These are the source token IDs. Then we have mask, which is the attention mask, indicating to the model which token should be attended to. Then we have the model forward pass that is happening. So the model computes the output given input IDs, attention mask, decoder input IDs, and the labels. So, and the first element of the outputs is considered as the loss. And coming to the logging, which is happening here, every 10 steps, we log the current epoch step and loss that is computed using the previously defined training logger and print it to the console. Right, and we have the optimization step here. So optimizer.zero grad clears old gradients. Otherwise, they would accumulate and we would be consuming more space. So the training, given the limited resources that we have, we would be exhausting all of it without the training to be completely finished. Then we have loss.backward, which is right here. Yeah, computes the gradient of the loss with respect to the model parameters. And then we have optimizer.step, which updates the model parameters based on the gradients. So this function overall encapsulates the core training logic for sequence-to-sequence models in PyTorch and demonstrating how to prepare data, execute a model forward pass, compute loss, and also update model weights. Let's execute this piece of code as well and move on to the next one, which is the validate. So in the validate function, this is basically designed to evaluate a trained model's performance on a given data set without updating the model weights. Updating the model weights happens in the train function, which we talked about just now. And in the model weights, we do not want to update, in the validate function, we do not want to update the model weights. It's used to assess how well the model generalizes to unseen data. And here is a breakdown of the components and functionality that we'll go through in detail. Right, we talked about the purpose of the validate function, and let's go through the parameters that it takes. Again, it has the epoch, which is the current epoch number used for logging. We have the tokenizer for decoding token IDs back to text. And we have the model, the neural network model that is being evaluated, which is our already trained CodeT5 that is coming from the train function above. Then we have the device, which we already set it to as GPU for faster computation. Then we have the loader, which is providing batches of validation data. Okay, let's go into the function in detail now. We have the model.eval, which sets the model into evaluation mode, disabling training specific behaviors like dropout. And it also, so we have two lists here where we want to store the predictions, and we also want to store the actuals in order to compute the loss and so on. All right, then we have the torch.nograd, which ensures that gradients are not computed during the evaluation, reducing memory consumption and speeding up processing. Then we are doing the batch processing here, which iterates over batches of data from the loader, similar to what is happening in the training function. For each batch, we move the target IDs by source IDs and attention mask to the correct device, which is the GPU. Then we use the model.generate function to generate predictions. This function takes several parameters to control the generation process, such as mask length, such as max length for the maximum length of the generated sequence. It takes number of beams for beam search, and others like repetition penalty, length penalty, and so on. So all these parameters are used to define the quality of the generated text. You can actually change these parameters during the lab session and find out how the model's output is being changed. We'll be doing that in another notebook, which I'll also talk about. So you can play with these values in that particular notebook. Then we are decoding and storing the predictions, basically. So that is what is happening in this block of code. So it decodes the generated tokens, token IDs back to text using the tokenizer, ensuring special tokens are skipped and extra spaces are cleaned up. Both predictions and actual target text are stored in lists for further evaluation, what we have seen previously. And we have the logging process as well that is happening here specifically. We log progress every 10 batches to provide feedback during evaluation, and we also return the results, which are lists of predictions and actual target text for further analysis, such as calculating metrics to assess model performance and so on. We'll be talking about the evaluation much more detail in the slides in the form of theory. instead of code, so that we get to see how well different language models are performing for the task of plan generation. Right. Some key points that we might want to consider, especially in this code, are regarding the beam search, especially, which is, I mean, we put numBeams as the parameter. The numBeams parameter controls the beam search size, allowing the model to explore multiple prediction paths and choose the one with the highest overall score. This often leads to better quality outputs. As I said, we'll look at this in action in another piece of code. Then we have the penalties. One is the repetition penalty and the other is length penalty. Are used to discourage the model from repeating itself and to influence the length of the generated sequence, respectively. And when early stopping parameter is set to true, it can halt the generation once all beam search hypotheses reach the end of sequence token, potentially speeding up generation, but we have disabled it here. We can try it out with false as well and see how the output is changing. Then we have the main piece of code where everything is coming together and we are training the model. So this, okay, yeah, I forgot to execute this block of code, right? And this is the main code where everything comes together and we make use of the previously two functions that we have seen, which is the train and the validate. Okay, so going into the code, first let's talk about the hyperparameters that are being passed to this function. We have the data frame, that is a data set that we have uploaded over here. Then from that data set, we want to extract the source text and the target text. So to give an example as to what our source text in this context would be, it would be the planning problem that we want to give as input to the model, and the target text is the plan that needs to be generated for that particular planning problem. Then we have the model parameters, which I'll talk to in the code block right after this. And we have the output directory where we want to give a path to save the fine-tuned model. Then we have the random seeds, which we want to set in order to have reproducibility of the experiments that we perform. Then we have the console logging in order to see the status of fine tuning of the model. Then we define the tokenizer, which is robot tokenizer that we talked about before. And we have the model. We are passing the T5 for conditional generation, and we have the model defined in the hyperparameters. So I'll talk about that in a bit. Then we move the model to the device that is set to GPU prior. Then we have another console logging just to inform as to where we are currently at in the piece of code when we run this cell. Then we have the data frame where we are extracting the source text and target text that I have just mentioned. Then we are displaying just two entries in order to see how the data set looks like. And for specifically this particular lab, in order to execute this notebook much quicker, I am just using the training function and not the validation. But traditionally, it would be something like if we put train size equal to 0.8, then 80% of the data would have been used for training and 20% of it would have been used for validation, which is ideally the scenario if you want to train an actual model that you want to deploy for real world applications. In our case, we just want to see how the code is working. So let's just do the training, and the validation or the inference, I'll talk about it in a separate notebook. And that is the reason I'm not going into the validation aspects of it in this particular notebook. Then we have rudimentary code over here, which is basically training, saving the train data split and the validation data split. I currently commented it out because we do not have any validation data set percentage. Then we print whatever we have obtained, basically the shape of the full data set, the train data set and test data set. Then we have the training set where we are passing to the planning data class all the required hyperparameters and to the val set as well. Again, this is we are not using the validation data set for this particular example, but you can try with that at a later stage as well. by modifying just this particular number, you can set the train percentage and validation percentage. Then we define the training params and validation params that are needed. And we define the optimizer, which is Adam, that is used as a standard. And the learning rate is coming from the hyperparameter block that is following this particular piece of code. Then we start the fine tuning. We record the time in order to understand how long the model has taken to finish fine tuning. Then we are running it for multiple epochs. Again, excuse me, the number of epochs are going to come from the hyperparameter definition. So we are running the train function, which we have seen earlier, multiple times. That is based on the number of epochs that is given in the hyperparameter definition. Then we record the time and we save the model to the output directory that has been initially mentioned in the code. Then we have the evaluating test data set where we run the validate function that we have discussed earlier as to how it performs and what results it produces. Then we are saving the output in a CSV format along with the actuals and the predictions for further analysis. This is basically what this code is doing. Let me run this one so that we can move on to the next, which is the hyperparameter definition that I was talking about. So the model that we are using is CodeT5 base. You can use any Hugging Face language model and substitute it with this code that works for sentence to sentence translation tasks, be it summarization, be it question answering, etc. Right. Then we define the train batch size, the validation batch size, which doesn't apply in this particular case, but you can leave it as it is. Then we mention the training epochs, which is just 3. Then we mention the learning rate, the max source text length, which is 512 tokens, and the max target text length or the output text length, which is 200 tokens. The seed is 44. So if we keep 44, we would be seeing the same performance throughout when we again execute this model. Let me run this particular code as well. Okay. Now this data set has around 16,000 data points, if I remember it correct. For the sake of time, I'm just taking 10 data samples, and my source text and target text are defined as based on the column names that are present in this particular CSV file or dataset file. And we do the model param definition, which is coming from here, and the output directory to save the fine-tuned model. And let me just run this piece of code. So the CodeT5 base model is currently being downloaded. It consists of these different individual files that is needed. And the PyTorch model.bin file is the pre-trained CodeT5 base, which is trained on, I think, 9 different programming languages such as Python and so on. Right. The training has already finished if we just take 10 samples. So this is pretty quick. But yes, you can experiment it with a different number of training data points and also include more number of planning domains. We currently just looked at blocks for and fine tune this model in order to see the kind of results. So this is the source text and this is the target text. This is how it looks like. It is tough to understand from this particular table, but we'll look at a better visualization for this in the very next code block, in the very next notebook that is present. That is all for this notebook. If there are any questions, you can reach out to me via an email or ask Biplav, who is going to be present there at the lab in person. Thank you very much.